Hi, welcome to Marker Board Videos. Today we're going to talk about collisions and momentum and impulse and how that all fits together. So first let me give you a little bit of information about collisions. If two objects collide in the absence of external forces, then the net momentum of the objects that they had before the collision is exactly the same as they have after the collision. And mathematically that's really important. That's also really important so that we can figure a whole bunch of stuff out in physics. Police officers use this all the time to determine car accidents and how fast a car was going before it got in the accident, based on how far it traveled and a variety of other details. But basically, the momentum before a collision is exactly the same as the momentum after a collision, and we're talking a system. Okay, we're talking a system, not just an individual piece of a system. So let me give you some examples. There's two kinds of collisions we're going to talk about. The first one is called elastic collision. Elastic collisions. An elastic collision is what happens when you have two things that hit each other. They don't stay together, they bounce apart. Now, they don't necessarily bounce in opposite directions, but they bounce apart. Here's three examples. We're going to do, this is the before, during, and after. So the black sample, you have a ball on the left is rolling, and the ball on the right is not rolling, it's sitting still. This one hits that, they hit together, and then the ball on the left stops moving and imparts all of its momentum and all of its velocity to the ball on the right. That's one example of an elastic collision. Another example is you have the ball on the left rolling towards the right and the ball on the right rolling towards the left. So the balls are rolling towards one another. They're coming at one another. They hit and they bounce off and they go in opposite directions. So they start coming together this way, they hit and they go back out that way. That's a second kind of elastic collision. And the third kind is you have two balls rolling in the same direction, only one is going a lot faster than the other, and it catches up to it, it hits it, it imparts some of its momentum, some of its velocity to the second one, and the second ball rolls off. So here they're both rolling together. You can look at the vectors to see the relative size of the speed or velocity. They hit, and then the first one, the one on the left, ends up going slow, and the one on the right ends up going fast. You kind of like give somebody a shove, kind of, if you will. That's three examples of elastic collisions. Momentum is conserved. However much momentum we have here, that's the same as the momentum we have here. Now it's distributed differently, isn't it? Because right here, this ball has zero momentum, and right here, this one has zero. So the opposite has zero. So it may change the distribution, but the sum is going to be exactly the same. Other kind of collision that I want you to know about is inelastic collision. Inelastic collision. And an inelastic collision, two things come together and they stick together and then they move off as one. They don't bounce apart. They stay together, kind of like as if they're Velcroed together. So it's kind of hard to show with balls, so I have two different ways of showing it. First, this is before. The ball on the left has a velocity and is moving towards the ball on the right. The ball on the right has no velocity, sitting still. They hit, they stick together, and both of them move off together to the right. Okay? Kind of hard to visualize that, I think, so we're going to do box cars instead. I don't know if you've ever seen them put box cars together. It's actually pretty amazing. They have this massive box car and this other massive box car, and one of them is moving. So let's say the one on the left is moving with a velocity of 6 meters per second. It's moving towards the right. And the one on the right is just sitting there. Now they have to have exactly the same mass for my sample. In real life they don't, but for my example they do. So pretend like these have exactly the same mass. The one on the right is moving towards the one on the left is moving towards the one on the right. During the collision they simply hit together and they stick together. And they really do that. They have those joints in the middle that hold them together. It's pretty cool to watch. So they're stuck together, and then afterwards they both are stuck together. They're moving together to the right with a velocity of 3 meters per second. Again, that's only going to be true if this one started out at 0 and if their masses are exactly the same. So elastic collision, they bounce apart. Inelastic collision, they stay together. Inelastic, they stay together. So most collisions involve external forces. Usually it's friction. So you're not going to see a lot of perfect collisions where in real life that it's exactly perfect, because you have friction, you have air resistance, you have acceleration due to gravity. But you know where you can see it? You can see it in space. Microgravity is actually what we have on the space shuttle and the space station. And so you'll see a lot of experiments done in 0G or in low G so that they can see the effects. And they find that exactly what we've said, the momentum is conserved in collisions, is exactly true when you're in space. Here on Earth, it's a little bit harder to see. Perfectly elastic collisions, boing boing, those bouncy ones, are not common. Some of the things that you will find is if you drop something and it bounces off the ground, there's probably going to be a little bit of a heat difference. It's going to probably heat up a little bit, and that is a form of energy, and that means it's not a perfectly elastic collision. You'll also hear a sound. Sound is also a form of energy, and that's one way that you can distribute your energy a little bit and your forces a little bit so that you don't have a perfectly elastic collision. However, if you look on a microscopic level and an atomic level, you'll see that they are perfectly elastic collisions between the atoms and between the protons and neutrons and electrons. Perfectly elastic collision. So that's one example where you will see a perfectly elastic collision. But in our world, for what we're able to see with our naked eye and experience, we're not going to see perfectly elastic collisions.